for briefing this with your kind permission. Professor Sakthivel sir is presently working as Professor and Head School of Physical Sciences since January 2020. Previously, he worked there as Associate Professor from January 2016 to January 2020. Assistant Professor in Delhi University from November 2010 to January 2016 till the joining of School of Physical Sciences. He also acted as Senior Manager R&D Reliance Industries Limited for 2 years. He has passed MSc in Chemistry at VHNSN College Madurai in 1997, got PhD in Chemistry from IIT Mumbai in 2002, and postdoctoral fellowship from 2002 to 2008 from different universities of various countries. Material science is his specialization and expertise core area, with development of eco-friendly heterogeneous catalysts for fine and petrochemical processes and nanoparticle synthesis and their uses. Sir was awarded with many awards with FRSC from Royal Society of Chemistry in 2019, Maya Devi Juneja Young Scientist Award in 2017, Dr. Sistla Kameswari Young Scientist Award in 2015, Japan Society for the Promotion of Science JSPS Fellow from 2006 to 2008, and many more. He also authored 4 patents, 3 international reports, and 102 research papers to his credit. He published 106 research articles in international journals, 32 H-index, and total citations of 3056. He has written 5 numbers of book chapters and 1 book. 5 number of students has already got PhD, and 5 numbers are continuing under the special supervision of Professor Sakthivel sir. We are highly thankful to you, sir, to being associated with us. Now I take the honor to introduce our resource person of second session of the webinar. In brief, Professor Dr. Prodeep Phukan, Professor, Department of Chemistry, Guwahati University, Assam. His focus on the topic surface functionalized magnetic nanotechnology, nanoparticles for the catalytic applications. In second session, who are with us to deliver his talk. The detailed introduction of Professor Phukan sir will be at the beginning of his talk. Now it is my honor to introduce our respected principal cum chairperson of this webinar, Professor Adhikari Lakshminarayan Das sir, who took over this responsibility of this institution since March 2019. With a very short span of time, he is trying to his level best to make this institution an unique one among the different institutions of Odisha. He has not only a very dynamic personality, but also a multifaceted leader whose continuous support and inspiration make this institution a glorious one. We are proud enough to work under you, sir. Now I request him to welcome our guests and participants to this webinar and say a few words regarding the college and this webinar. Professor Adhikari sir. Sir, kindly unmute and say something, sir.
Thank you, Dr. Parida. Very good morning to all of you, those who are with us for today's seminar. Once again, I welcome all the participants, resource persons across the country and from the different parts of the world to this institution, Pattamundai College. Here I just want to say that our college has already completed 50 years and we are now 51 years old institution where 4,000 students are reading. We have 14 departments, 14 honor subjects, and a very green area, having a very good plantation inside the college campus. If one person will visit this institution, he will definitely astonished and glorified that this institution has done a lot to providing pure oxygen to the climate. So it is my proud and it is the proud of our college that we have very nice and resourceful persons, two resourceful persons for the today's webinar. It is the only blessings of the COVID or the Corona that we could have get two eminent, resourceful, and intelligent persons having such a good background to attach with us. Otherwise, it is not possible to bring them to our institution for this national seminar. Within a very short span of period, they have given their consent to have with us and to deliver a very nice presentation to our participants. So while I go through the CV, the biodata of Dr. A. Sakthivel, the professor of our Central University of Kerala. I simply amazed that he has done a lot for our country and he has done a lot for the chemistry. Here I want to mention that many eminent persons, alumni, students are with us in today's seminar. A person who was retired from ISRO, Dr. Fakir Pradhan is also present with us. I welcome him to this seminar on behalf of this Pattamundai College, sir. So I was talking about Dr. Sakthivel, who has done a lot, read a lot, researched a lot, guided a lot of students for their career development and the research project. Once again, I welcome Dr. Sakthivel sir to this seminar, national seminar, and you just present a very nice deliberation today. I hope. Again, I also welcome Dr. Prodeep Phukan from the Guwahati University, the Professor Prodeep Phukan, who is not only a young person, but has a commendable job towards the chemistry, Department of Chemistry of the Guwahati University, and he has, I have seen his biodata where I got that he has already, that 28 scholars has already got PhD under him. This is a very commendable one. Sir, we are very much proud that you have given consent with us to remain with us and give your deliberation in the second session. I hope all the students, all the participants, all the research scholars who are with us will be no doubt benefited. But here I request all of them, please mute your audio at the time of deliberation of our resource person, and whenever you require any interaction, the resource person will ask you, then you can unmute, otherwise it will be disturbed. So it is very nice good morning to all of you, and I welcome all of you to this national webinar. Thanks to all.
Thank you, sir. Now I request Professor Sakthivel, sir, to start his talk to deliver, sir. Professor Sakthivel, sir, kindly unmute and deliver your talk, sir. Sir, please.
Hello, can you hear? Can you hear? Am I audible?
Yes, sir.
Okay, thank you. So, is it slides are visible?
Yes, sir.
Okay. First of all, I like to thank the organizing committee, in particularly the principal of Pattamundai College, that is Professor Lakshmi Narayan Das, and Dr. Farida for the very elaborate introductions. I thank you for inviting me and then gave opportunity to present some of our research work, to share some of our research work. So I thank you, first of all, inviting me to share some of our research work. So today I will be going to talk about a few aspects which we developed last 1 decade, like from Delhi University, and here what we are doing it, that I am going to talk about it. And since this talk, I understood that there are a lot of MSc students also there. So initially I will cover some of the fundamental aspects of zeolites, because today talk I am going to cover the role of zeolite and zeolite-like molecular sieve material as a heterogeneous catalyst and the significance on various chemical transformation. That is what I am going to cover today. So before going to my talk, I just want to just show about our university. See, we are located in the Kerala. You know that Kerala is located in the extreme south of the Indian map, Indian geography, and in which our university is located in the border between the Kerala and Karnataka. So it's the nearest airport is Mangalore airport, and nearest Mangalore and Kannur is, we have 2 airport is nearest airport. And then this university has established in 2009 by the MHRD. And then the main campus, that what we have shown that map, which we can see that it came in 2018. That is just 2 years before only we moved to this main campus. Before that we were in temporary campus. So this is our university geographical location. And now currently we have the MSc chemistry, as well as we have the PhD chemistry course. And we also soon we are going to introduce a integrated MSc, as well as there is a BS program, 4-year BS program as per the NEP policy. We are going to maybe probably by the next year, next academic year, we may introduce the new 4-year BS program also. So this is all about our university, brief about our university. And before going to talk about the today talk, I just give an overview of what we are doing in our research laboratory. So we are focusing on mainly our work is focused on the development of heterogeneous catalysts. That is what do you mean by heterogeneous? There are catalyst is basically it is a promote the reaction equilibrium to a desired product, to get a desired product. So in which there are two types, we know that one is homogeneous catalyst, sorry, and other one is heterogeneous catalyst. So homogeneous catalyst, normally the reaction as well as catalyst the same phase, for example liquid phase, both in the liquid phase, then they're called as a homogeneous catalyst. When the catalyst in one phase and the reaction in another phase, for example catalyst in the solid and reaction going to be taken in the liquid phase, then it is called as a heterogeneous phase. So we are focusing on heterogeneous catalyst development, and in particularly we are focusing on development of heterogeneous catalyst for various organic transformation, which will many chemical processes. That is what our ambition, our focus is on that. In which we are developing three types of catalyst developments. One is what you call as here I showed, that is a zeolite type catalyst. It is basically we are preparing different types of zeolite and zeolite-like molecular sieve. What is zeolite? What is zeolite-like molecular sieve? I will come to the definition later after my talk. So what we are doing is we are trying to develop a different types of porous, nanoporous and nanostructured. It's not a nano size, but it is a nanoporous and nanostructured materials we are preparing. And then we are preparing these kind of materials, and then we try to look into the various chemical process, like for example, the conversion of biomass component to valuable chemicals, then utilization of CO2, carbon dioxide, then hydrogenation, then isomerization, heteroisomerization. These are some of the process where a significant role in the petrochemical industry and fuel production. So we will also today talk about some of the process on this one also. So this is our one of the area of work we are doing it. That is, we develop a zeolite and zeolite-like molecular sieve materials and explore this kind of catalytic reaction. So mostly this is a tetrahedral framework based materials. Then another material we also work on that is a heterogeneous catalyst, again based on the mixed metal oxides. Mixed metal oxide we prepare from the layer materials, and then we explore for the various application, various chemical application, as we have demonstrated here. Hello. So then we also, another part of the work we also develop on a heterogeneization of homogeneous catalysts. So we know that those who are studied in chemistry, the organometallic catalysis, organometallic complexes has been play one of the major role in the fine chemical synthesis in particularly. So so when you talk about fine chemical synthesis, so you can organometallic complexes play a major role. So we also focus on those kind of organometallic complexes, like for example furfurin and furfurin types of derivative, and then cyclopentadiene type derivatives, and mobilize on the surface and then explore for catalytic activity. So overall, my research group is focused on development of heterogeneous catalysts and then its application for the various organic transformation, which is value added to chemicals, and which is value added process, and which is utilized for environmental process, which is utilized for the energy resource. These are the main objective of our research work is going on in my lab. But today I'm going to talk about mostly based on the molecular sieve based catalyst, that is zeolite based molecular sieve based catalyst, or zeolite like molecular sieve based catalyst, which I am going to talk today. So before going into the zeolite molecular sieve and its property, first because I feel that that audience mostly comes from the MSc level or some college students level there. So I just give a brief overview about how we can visualize this molecular sieve. What is their significance, importance? That I will discuss briefly, very briefly I will discuss. So when you talk about molecular sieve, before going to the molecular sieve, first we should know that what are the development in the solid state chemistry. Because when you talk about heterogeneous catalyst, it is again based on the solid state aspects, that is solid state chemistry. Heterogeneous means it is a solid and liquid interaction or solid and gas reaction. Of course, recently there is a liquid and gas reaction also is taken place, but mostly if you take it, heterogeneous catalyst means it is basically interaction between the solid and liquid or solid and vapor. So mostly inorganic mixed metal oxides and other oxides, other oxide and hydroxide types. So normally the solids are classified into two types. One is either based on the long range ordering, it can be crystals or it is amorphous materials. That's how it has been classified. And if you see that last 100 years, there are several development in the solid state chemistry which lead to the lot of application in the solid state chemistry. The very recent application is, you know that everybody, nano materials and nano energy storage device and nano functionalized materials. So these are the most important or recent development in the solid state chemistry. And when you look into the solid state materials or chemistry, first always, for example, if you talk about inorganic materials or inorganic salt, even if you take simple inorganic salt, sodium chloride, how we visualize normally how the atoms are packed, how the molecules are packed, how the anions are packed, and then how the cations are present in the voids. This is how the normally visualize the solid state. Then based on the cation by anion ratio, it will form the different type of crystal structure. Because it is important to know the nature of crystal or nature of surface to understand the catalytic property. So that's why I'm just starting from the fundamental aspect, and then I will go into, mostly we will be focusing on that silica based system, that is a SiO2. So normally we visualize the materials, inorganic material or inorganic oxide, visualize through the close packing system. However, there are other way one can visualize the structure and material aspect and property, that is based on the what is called as a polyhedra. What do you mean by polyhedra? So we can see that here the polyhedra, there are how the atoms are close packed in a proper geometry. For example, here is a tetrahedral polyhedra. The other one is a octahedral polyhedra. This is how the geometry has been oriented. Based on that, we can also visualize. See, initially, when you talk about inorganic materials or oxides, we can visualize through the close packed system. But there are certain materials which can be visualized through the what is called as a polyhedra. Why we are coming to the polyhedra? Because the chemistry, whatever we are going to talk about it, it is basically on how to visualize the structure based on the polyhedra, how the active sites are created in the polyhedra. That's how we are going to visualize. That's why I am giving the brief introduction about the what is called as a polyhedral visualization of the inorganic material or heterogeneous catalyst. Okay. So when you talk about polyhedra, see how the atoms are close packed. The same way, we can also see that the polyhedra, how it can be close packed and form the close cubic or close arrangement. So here is some of the examples. So one of the best example of polyhedral packing or polyhedral connection is the nothing but silica. Because see, if you see the silicates, silicate is basically, so you can see that there is a 4 oxygen anions which is surrounded. Silica is located in the cavities created by this 4 oxygen ion, that is tetrahedral voids, and this whole unit has been visualized as a tetrahedra polyhedron. Okay, tetrahedral polyhedron. So now, in general, the inorganic materials can be visualized either through the close packing or through the how this polyhedra is connected to each other. If you see that silica tetrahedra, the one great advantage is it cannot be edge shared or it cannot be face shared. It is only can be connected to one polyhedra can be connected to another polyhedra through the vertices. See, for example, in the previous slides, you can see that this is a edge. This is a octahedral polyhedra. It can connect through the edges and then it can form the closed compact structure. But then tetrahedra polyhedra, it will not form such a closed compact. So that means it will form the open framework structure. So it is called as a open framework structure. That makes that this material has been interesting. That is, silica based materials are interesting. So basically, this silica based material has been derived from the basic unit is like what we call as SiO4 4 minus, and how this polyhedra is connected to each other, and it will form the numerous structure. And you can see that whole earth crust containing based on the silica crust. Okay, silica based polyhedra connection. You can see that the earth crust having the 90% of the earth crust material is what we call as a silica based earth crust. Okay, silica based materials. They are all the most important things of this polyhedral silica network is it can be the silica form the three-dimensional network. Once if there is a three-dimensional network, then what will happen when we can substitute? See, you can see the silica sizes. This is the silica size, Si4 plus size. But when you put aluminum 3 plus, so you can isomorphously substitute. So what can happen is this silica framework, it can form that three-dimensional network form. It can form the framework. I will show the later structure how it is forming the three-dimensional network. When you form this framework, if you replace one of the silica with aluminum, what will happen? See, silica 4 oxygen is connected. Then this 4 oxygen connected to the another 4 atoms. So it is neutral. But when you take about alumina, it is connected to 4 oxygen, and this another 4 oxygen will have the connected to another atom. But aluminum is only 3 plus, but it is connected to 4 oxygen. So there is one residual anions are there. This residual anions will be replaced with a proton. This, when there is a proton is there, then it is used as a what you call as an acid catalyst. That how the silica matrix, the acidity is coming. This how the importance in this kind of material in the petrochemical industry. So in this kind of silica material, there are 2 types of materials are very important. One is what you call as a pillow silicate. It forms the layer structure. Okay, you don't worry about the structure. Don't look at too much complicated. What will happen? This is one layer like sheet. This is one sheet. This is another sheet in which you can have the cations, or it can have a proton, and it can have any other cations which can be used for the catalytic activity. The other one is the 3-dimensional. When this polyhedra, this is, you can see that each triangle represents the one polyhedra. So when the polyhedra is connected through 3-dimensionally, what will get it? You will get a 3-dimensional structure, 3-dimensional gauge, 3-dimensional pores. So that will make that this kind of material. See, what is the difference between this material and the simple metal oxide is simple metal oxide, when you take it, they are all bulk oxide where the surface area is less. But when you take about this kind of materials, we can have that there are open framework structures. When there is an open framework, mean there will be huge number of large surface area, because the molecules can go through the different pathway and can produce a lot of surface area. So that how the zeolite has the advantages. So in principle, that, or by definition, zeolites are like what you call as a, it is a highly crystalline aluminosilicates. So it is basically derived from silicates, but then when there is isomorphous substitution, then you will get a aluminosilicate phases. So it is a derived from the what you call as zeolites are called as a aluminosilicate materials. And this was first developed by the scientist, famous Swedish scientist called, he is a A.F. Kronstedt. He only developed this or coined this term zeolite. He coined the term from the Latin words, that is geo and boil, that has a litho and stone. That is a geo means litho and geo means boil and litho means stone. That is a boiling stone. What he come to know that when he tried to heat some of the minerals which is found in the earth crust, he found that there is a water is coming out, there is bumping out from the solid. That means the water pisses out inside, it's coming out when it's heated. It's look like a stone is boiling. That's how this terminology is proposed. So this how the zeolite chemistry has started, and the most of the chemistry, zeolite chemistry has application as a acid catalyst, as absorbent, as a molecular sieve. So that is what it started a major application. So one of the most important application is this zeolite material has a pore size ranging from 3 to 7 Armstrong. So it is a potential for absorbent. And then when there is a acidity, you are generating the acidity, because how much aluminum is there, that much proton you are going to generate. That acidity going to be useful for the petrochemical industry. So because, see, one thing we have to understand that till now we have gasoline in our whole the world having gasoline. It is because of the revolution given by the what is called as a zeolite, because it is called as a fluidized catalytic process. That is a catalytic cracking process by which you get a lot of gasoline from the petrochemical industry. So this is where the zeolite play a major role. So here the structure, you can see that the zeolite, it is a 3-dimensional network. You can see that how beautiful the network. It is like a spider web. So you can have the lot of channels. You can have the cavities. You can have the 3-dimensional molecular access. And also you can see that you can have the cation exchange site. For example, it has been used as an ion exchanger. So it has a very good cation exchanger site. So it has a lot of application. So how to visualize the zeolite in the best simple way? It is nothing but everybody's home as one zeolite molecules. So you have the room that is nothing but cavities. If you take your university, the corridor is nothing but channel. That's how we have to visualize what is zeolite. The zeolite, the corridor in your apartment. When you can take each. So there are 197 family. There is 1,000 millions of zeolites are developed. They are nothing but can be visualized like how our buildings are there. Okay. So it is like a porous materials. The zeolites are considered as a porous material, which is having the, you can see that these are the voids and these are the channels. So there is a channels and voids where the molecules can be trapped and then can be reacted and give the different kind of product. Like here you can see that how the methane absorption is there, then how the cation exchanger sites are there, how the some organometallic complexes are trapped inside that. So these are the different types of application zeolites are known. And you can see that some of the progress of zeolites, you can stay from the, this basically it's used from the absorptions, and then it is comes as a safe selective catalyst. You know that the terephthalic, hello? Fine? Hello? Yeah, it has been used as a safe selective catalyst, and it has been used as a catalytic cracking in the petrochemical industry. These are some of the major applications of the zeolite in the industrial aspects. And the most important point in the zeolite is it has a molecular sieve property. Molecular sieve property. What do you mean by molecular sieve? It is a porous solid or porous materials which can distinguish the molecule based on the size and shape. That is, when the molecules can distinguish based on size and shape, then it is called as a molecular sieve. So this kind of application, zeolite has shown a lot of interest. Okay. So coming to this molecular sieves, so the molecular sieve has been classified into 3 categories. That is, one is microporous, then other one is mesoporous, then third one is macroporous. So the molecular sieve material has been classified into 3 categories. There is microporous, mesoporous, and macroporous based on the pore size. If the pore size is less than 2 nanometers, it is called a microporous. When the pore size is in the range of 2 to 50 nanometers, then it is called as a mesoporous. So these two materials has a numerous application in the catalytic point of view. So because it has a very good porosity, it has a very good surface area, and it has a molecular diffusion limited. So you can see that this material not only silicate and zeolite. See, what we have discussed so far is what is silicate, what is zeolite. So it is not only silicate and zeolite based catalyst, they are used as a catalyst for the various petrochemical reaction. There are another class of material called as aluminophosphate. It is, see, aluminum 3+, phosphorus is 5+. Silica in the silicate is a silica 4+. So if you take 2 silica, which is equivalent to 1 aluminum plus 1 phosphorus. That's why the aluminum phosphate is analogous to the silicates. And that also shows a lot of application in the petrochemical industry. So we will be today, we'll talk about some of the important aspect of aluminum phosphate and then some of the important aspect of silicates we will be discussing. So here another slide I like to give this just to overview. You can see that zeolite has been used in this is a normal petrochemical process, how there are different steps involved in the petrochemical process. The green, wherever the green or gray-green point it is mentioned, those places, zeolite and zeolite-like material has been used. So you can see that zeolite purification, zeolite for separation, zeolite for engineering aspect, all other aspects. You can see that the petrochemical industry has been play a very, very major roles to generate the fuels, kerosene, gasoline production, all the cases it has been involved. For example, hydrodesulfuration, hydrodecracking, isomerization, reforming, alkylation, condensation. These are the different types of process which involve to give the gasoline and the products, where the zeolite and zeolite-like materials. For example, here you can see the zeolite-like material, like it is used as isomerization, hydrocracking, that is aluminum phosphate based materials has been used. So then before going to talk, already I'm covered a lot of things, the introduction only, but because this is so important, it is very important because one has to understand. So we can see that this zeolite and aluminum phosphate, you can see that zeolite is a neutral, zeolite is aluminum silicates, then aluminum phosphate is a aluminum and phosphorus equivalent to 2 silica, and it is also again the neutral molecules. But you can again, instead of aluminum, you can substitute silicon. It also generates acidity. So these are some of the materials property. You can see that they have a lot of pores. You can see the pores and channels and cavity. So this material has a lot of application. How they are prepared normally? You take the precursor like silica, alumina, or phosphorus source. Normally it can be prepared in presence of like a template. It is a template means the simple way visualize is whenever we build construct the building, how the sticks, wooden sticks are used, they are like nothing but template. Once you remove the wooden stick, you will get a rooms, corridor, and everything. The same way the materials, zeolite material will, after removing the template, that is organic normally used as a template. Once you remove, you can see that there is a cavity sun channel. This is how normally they have been prepared in a hydrothermal condition, and you will get this kind of porous material, you will get it. So this is how the material has been prepared in the general way. And another material that I said, that mesoporous material. So the difference between mesoporous and microporous material is, microporous material, the pore size is only 2 nanometer. Whereas the mesoporous material, the pore size will be 2 to 100 nanometer. That means microporous material, the template is only one organic component. For example, ethylene diamine or triethylamine, like one simple component. But in the case of mesoporous material, what will happen? You will be preparing in presence of surfactant. It will form the micelle. Again, it is going to form the organic molecules or play as a template or surfactant. Once you remove these organic molecules, you will generate the cavity. This is how the molecular sieves, mesoporous molecular sieves can be generated. But the difference is, mesoporous material will have the large cavities, but the microporous material will have the cavities are relatively small. But then microporous materials are very good crystallinity, but then mesoporous material, the white ball represents nothing but a hydroxyl group. So it is like what you simply visualize how it is like a clay house, how the clays are arranged. A clay house has a kind of softness. So the pores are soft, the pore walls are soft. Whereas this is a concrete house where it's like a concrete building where you can have the strong pore wall. So that's how the difference in the microporous and mesoporous. Now, okay, I'll just skip this mechanism. Now, coming to the aluminum phosphate, see, silicates are used very good in various petrochemical industry. The same way, aluminum phosphate, here is the aluminum phosphorus. So it is a tetrahedral. When you put aluminum, there is a negative charge created. So you get aluminum 3+. When you put phosphorus 5+, you will get a positive charge. So overall, this molecular sieve materials, aluminum phosphate materials are neutral. But you can substitute, when you substitute the tetravalent cations, then what will happen? You will generate the acidity. So this material, what is the aluminum phosphate material, is more advantageous compared to silicate is, it can have the flexible framework sides. The aluminum phosphate will have the more flexible framework than the silicates. So that lead to these materials are very interesting for the various catalytic application. But then their stability, here are some of the examples of these aluminum phosphate materials are shown. Anyway, these materials, as I said, that where the M is either metal or silica or any other material. So because it has a flexibility. Hello? Yeah, the aluminum phosphate will have a lot of framework flexibility, will give the lot of application also. Then this material, what is happening, the aluminum phosphate, because unlike silicate, aluminum can exist in both tetrahedral and octahedral coordination. That means the aluminum can come out from the framework easily and it will form as a bulk oxide. From the beginning, I said that whenever there is an open framework, when there is a huge surface area, it has a good for heterogeneous catalysis. So that's why if you have retained the aluminum in the tetrahedral frameworks, it will form the framework structure. When there is a framework structure, it has a very good application. So that's why it is important to retain these kind of porous framework structures. So how we can retain the framework structures? Because if you take the microporous material, it is a very good crystallinity, but mesoporous material, it is a very big pore size, but the molecule can accommodate, bulk molecule can accommodate, but there are large number of surface hydroxyl groups. So if you avoid this surface hydroxyl group, then we can have this material also will have a strong stability. So it is like I said that how this clay house, when there is a heavy rain, it can be collapsed. But then when there is a concrete house, it can sustain. But this house, this place, that mesoporous material has accommodate a bulk molecule because of the pore size is bigger. Then how we can make it? Can you prepare the meso micro composites? This is what our focus. We focus on that, how to prepare the meso micro composites materials so that we can have the good thermal, hydrothermal, mechanical as well as catalytic efficiency. So that was our main objective of this today talk I am going to talk. So like how we can make this meso micro composites. What we do is we prepare the microporous precursor. This is called as a precursor. Like how when you build the building, because we have to visualize the existing one so that we can visualize easily. When you build the building, you make the bricks, then you make the bricks, you assemble properly and construct a house. The same way, the microporous precursor act as a brick, that is a primary building unit, and then in presence of structural directing agent, or it is called as a template or surfactant. We can call as a surfactant because we are focusing on preparing a mesoporous materials. So when you prepare with this mesoporous material, in presence of the precursor and microporous this template, it will form the micellar arrangement, and there is a orientation of the molecules which gives that different structure. Either it is a hexagonal or cubic or different structure will lead with the porous nature. So here how we visualize. Here the like each that dot represent that there is a building unit and there is a channels. You can see that there is a hexagonal 4 channels we prepared. So these kind of materials we prepared, and then we try to utilize for the one of the important reaction like what we call as a isomerization of alkene, that is a 1-octene. Because see, the thing is in petrochemical industry, if you C8 hydrocarbons are very, very important in the gasoline production, because C8 having the branched hydrocarbons. This is especially the branched hydrocarbon. Here you can see that this branched hydrocarbon has a significant importance in the petrochemical industry. So when you convert this into branched hydrocarbon, which is most important for the gasoline production or efficiency of the or value added to the chemical, because linear hydrocarbon not have so much ignition ability, whereas the branched hydrocarbons have the very good ignition ability. So can we convert this into the, because we have a lot of linear product will be coming from the petrochemical industry, can we convert? So this is what we are going to mostly focus on that. Okay. So what we are trying to, first we try to prepare this material. Okay. So forget about these numbers. These are numbers are represented with the different types of primary unit, like how the bricks have the different structure. For example, if you go to the Kerala, if you come to Kerala, the bricks are quite big. But if you go to Tamil Nadu or some other place, bricks are smaller size. So it is like a, suppose 34, suppose 5, suppose 37 are like a primary building unit or secondary building unit with the different structures. So we build with a different structure by using the precursor like silica, alumina, and phosphorus. We build the different precursor material. Once we prepare, then we introduce a surfactant to form the mesoporous material. So once these mesoporous materials are assembled, then what will happen? We after the assembling of mesoporous material, simply you burn out this surfactants. You burn out this surfactant, then what you get? You will get a channels. So this is how we prepare the material. This is how we proceed for the preparing material of this material. Okay. So once we prepared material, now we have to understand that whether we have the meso and microporous structural property. How we can understand? We have to carry out with it various spectral and analytical methods. So first thing is always we look into that. We look into that FTIR spectroscopy, because you know that FTIR is a very good fundamental tools for the understanding the functional groups. So here in the zeolite, the functional group is a secondary building unit. As I said that the bricks type, that double 4-member or double 6-member ring. So it is like a 6-member means 6 silica or aluminum atom. 1, 2, 3, 4, 5, 6 aluminum or silica atoms, which is connected to 2 6-member ring connected, how it is connected to each other. When it's connected to each other, there will be a vibrational band at 2 vibrational band. One is 560 and 640. So we could be able to see this vibrational band in our material, that we support that the whatever we prepared material having that secondary building unit, that is a zeolitic nature. This is nothing but a zeolitic nature we confirm through the normally through the what you call as a from the FTIR spectroscopy. Then we'll normally study with the, how this, I told that this material whatever we develop is a meso and microporous material. How to confirm the meso and microporous material? So the best way to confirm the meso and microporous material is what you call as a surface area analysis. You know that, see, it is nothing but how the nitrogen is absorbed at a liquid nitrogen temperature. So when you look into this one, at P by P0 is below 0.1, there is a sharp uptake of nitrogen. What does it mean? Means, see, you have very narrow channel, very, very narrow channel. When you have narrow channels, only one monolayer of nitrogen is going to absorb. So whenever it's small narrow channels, the monolayer is absorption, there is a condensation of nitrogen at P by P0 of 0.1 will occur. So that is where it is going to be happen in the P by 0 below 1, that is support that this is a microporous nature. Then there is a multi-layer absorption. You can see the continuous nitrogen uptake is there in the range of P by P0 range, that is relative pressure range 0.4 to 0.6. That indicate that you have there are the pore sizes are quite broad. You have continuous molecules are absorbed, and then there is a pore filling, is capillary filling. You can see that capillary action. So capillary filling is occur. That's why it's called as a capillary filling of the molecules, and it form the meso-micro composites material. How this is going to form, you can see from here. So that our whatever material is formed is a meso-micro characteristic nature. So which we normally confirm with the surface area. You can see the surface area is almost 500, and there is pore size around 3 nanometers. And because micropores is like a bricks, it doesn't show the pore size. It will be on the wall, so it doesn't show any pore. So you can see that the pore size is about 3 nanometer, which indicate that our materials are mesoporous in character. Okay, and you can see that normally the mesoporous character, normally we can look at from the what we call as a HRTM image, that is a transition electron microscopy. You can see that the TM image shows that the uniform channels, there is a porous, that you can see that there is a white and black spot. That the black spot is nothing but porous, and there is in the EDAX indicate there is a white spot. It will represent how the atoms are arranged. And this, see, you know that if it is materials are mesoporous or if it is materials are amorphous in character, you will not get a spot pattern in the ED pattern. That is, it is called electron diffraction pattern. So which will tell that where the atoms are present, how the atoms are arranged. So we can see that the presence of spot pattern is indicate that the atoms are arranged in the uniform fashion, and it is a very good crystallinity this material having. So that is what indicate that the structural aspect. Then see, as I said that this material have the acidity. So how we confirm the acidity? Normally this material can be confirmed the acidity through the pyridine absorption methods. So normally pyridine is a 5-member, sorry, I couldn't show the pyridine structure. So what will happen when the pyridine has aromaticity. So when it's connected through the aromaticity, through the metal aluminum center, then it's going to form the Lewis acidic sites. And when there is pyridine form the NH proton, that is a pyridonium proton, NH proton, then it is called as a Bronsted acidity. So if the surface, normally how the acid-base titration, sulfuric acid versus sodium hydroxide we titrate, the same way, it is kind of titration at a different temperature. So when you do that different temperature titration, when you do that, the presence of, if it is, you have the Lewis and Bronsted acid sites are there, then we can see that the FTIR spectra will show the peak around 1440 and 1540. The 1540 corresponding to the Bronsted acidic site and 1440 corresponding to the Lewis acidic site. So from that we confirm that if the acidity, the peaks are retained even up to 500 degrees centigrade, means the acidities are very, very strong. It shows the strong acidic character of these materials. That's how this can be confirmed with the materials. So this is the basic way we confirm the surface acidity. Okay. Now coming to the reaction part. See, so as I said that normally linear hydrocarbon has the less important compared to branched hydrocarbons, because if you see the value, the bracket indicate the what is called as the octane value. That is the ability to ignite the hydrocarbons, because the gasoline, the molecule should be ignite under the ignition condition. So if the more the octane value, it will be good efficiency for the fuel. So how we can convert the paraffin, like a linear hydrocarbon, to branched hydrocarbon, which is one of the important aspects. What we did, we explore this our material with the hydrocarbon, that is isomerization of 1-octane to mono and bi-branched or multi-branched hydrocarbons. And we have studied with this reaction with it. Normally, catalytic heterogeneous catalysts, always reactions are relatively high temperature. Normally, the reactions are carried out with what is called as a fixed bed reactor. That is it is called not like a simple RB, round bottom flask. Normally, we do any reaction, we think about round bottom flask and then do the reaction. Here it is like a kind of, you can assume that there is a glass rod or what you call as column. People, you do the organic people do the column the same way. We have the packed column in which the catalyst will be packed. How your organic elute you are passing through, the same way we pass through the catalytic reaction mixer. For example, 1-octane we will pass through the bottom, and then PET will have the packed column will have the temperature in the range of these are the different temperature, and then flow rate of flow will be, there is a WHSV is nothing but weight over space velocity. It is how fast the molecules are moved. 8 means it is a slowly the molecules going, that is a reactant molecule slowly go. slowly go into the catalytic bed and then react. Whereas when there is WHS is high means the molecules are move very fast. So based on that, we will be checking the activity. So we can see that initially in all the cases, we can see the up to 90% conversion when there is a short, when there is a more contact hours. WHS is, that means within 1 hour only 8 ml has been passed. That means you have the more contact times. So more contact times, then the select conversion is 90%. But then you can see that the branched isomer selectivity is only 30%. But we need to have the more branched isomers. So how to improve it? So we try with the different methods. So you can see that we tried with a different temperature also. But then we can see that in most of the cases, the branched hydrocarbon selectivity is in the range of 30 only. So for example, we then later what we do, we choose the best active catalyst. For example, we choose the catalyst which shows the best branched hydrocarbons. Here is you can see the together 40% branched hydrocarbons. Although conversion level is 80 and 88 is not so much different, because when you look into that, anything above 50 is good. So we have 80%, and then we have a 40% branched isomer selectivity. So then what we did, we try to improve the branched isomer selectivity by improving the strength of the acidity. How we can improve the strength of the acidity? So normally the material whatever we prepare will have the kind of some kind of porous nature or some kind of defect sites will be there. So these defect sites will be controlled with treating with the tetraethyl orthosilicate, that is a silica, additional silica, and then we get a best defect-free materials we can get it. Once defect-free materials by introducing with the silica, then we can have the more of acidity that will be helpful for the improving the isomer strength. So here you can, this is how the pyridine will be coordinating. So the Lewis acidic will be coordinating like this, whereas Bronsted acidic sites will be coordinating like forming through the prudonium ions, which can be evident from the IR spectra. So once we improve the silica treatment, we can see that the Bronsted acidity is improved quite a lot compared to the previous case. So once we improve the Bronsted acidity, then we can see that the overall branched isomer selectivity, here is the mono and the di branch. So overall branched isomer selectivity, you can see that it can improve up to 60%. That means you are improving the branched isomer selectivity, you are improving the conversion with the improving the acidic strength. So this how the one can tune the properties of the acidity of the materials by just tuning the various treatment like introduction of silica, introduction of alumina, and other treatment, we can do it. This is how we have done. And then reaction kinetics, it shows that the reaction is facilitated. We have studied kinetics by the different finding out the rate constant at different condition. We can say that there is a K1 is much lower. That means it is a linear isomerization of this A to B is very more favorable. And then same way there is a conversion of converting C is quite difficult, but once it's forming the C, it can convert it because K6 higher than K5. So once the C is forming, the C can be converted into D quite easily. That is, we can identify from the activation energy. So overall, this reaction has been facilitated with the control with the rate of reactions. So formation of mono branches, linear branches is quite easy, but getting the bi branch will be quite difficult, but it need a very high temperature. That's what we understood. Then, okay, I just briefly overview. Besides, we also work out some of the base catalyzed by introducing organofunctional groups, which I skip it. Then I skip because of the time. I just one more things I'll tell you. This kind of molecular sieve material also good for the heterogeneous of homogeneous catalysts. Just a few minutes I will talk about this one and then I'll stop. Okay. So how, because this kind of molecular sieve material is one of the good catalysts which we have shown in the previous slide. And this kind of heterogeneous material is used for the anchoring of homogeneous catalysts. For example, you know that cobalt carbonyl is one of the best or commercial catalysts for Otto-Rowland process. Homogeneous organometallic complex, if you have studied, you might be know that it is a cobalt carbonyl is one of the best catalysts for the hydroformylation of olefin. So, but then cobalt carbonyl we cannot handle. It is a volatile. It is a cobalt in 0+ oxidation state, 0 oxidation state. It can immediately decompose. So what we did we modify this material, this kind of molecular sieve material. We modify with some surface functional group. especially alkyne, that is triple bond containing functionality we modify. So the one interesting property is whenever there is alkyne moiety is there, metal carbonyl form the bridging complex with this kind of bridging complexes will be there. So once we prepare this kind of bridging complex, then what will happen? The metal carbonyl can be stabilized, and then this metal carbonyl stabilization we can handle under nitrogen atmosphere without decomposing these materials, and can be useful for the heterogeneous heteroformylation catalyst. Because this is the first example on heterogeneous heteroformylation catalyst which we have shown as a potential application. So the presence of metal carbonyl you can confirm from the what you call as a from your FTR spectra. So we can see that once cobalt carbonyl is loading, we can see the strong intense band around 2100 which support that the presence of carbonyl band. Okay, and then this reaction heteroformylation, it is a olefin converted into formyl group introduction. This is another important reaction in the petrochemical and fine chemical industry to introduce the functionality, because it is olefin. You are introducing carbon monoxide, CO functionality you are introducing into the molecules. It is one of the most important study in the industrial aspects. So you can see that this kind of complex will be converted into 97% conversion. It is carried out in the liquid phase heterogeneous catalyst. So here the high pressure liquid bed reactor, where the reaction has been carried out to 100 bar. Basically, you can see that the reaction is carried out around 100 bar at 8 hours at 100 degrees centigrade. We can see that the catalyst can be converted to our olefin into heteroformylated product about 97%. It is carried out at 65 bar. Sorry, not 100 bar, 65 bar. It can convert into 97% conversion with a heteroformylated product 91% and hydrogenated product alcohol will be 8%. So you can see that these are the product distribution. So this kind of material also good for the supporting system. So these are the some of the aspects we are doing it. Besides, we also do with like molybdenum carbonyl, which is used for the crafting of molybdenum carbonyl also, which we use for epoxidation, olefin epoxidation. We can see that we also studied when you do the molybdenum carbonyl, it will convert into molybdenum oxo species when you treat to the hydrogen peroxide. They are also used as one of the good catalysts for the epoxidation catalyst. So this kind of material can be used as a good catalyst as well as catalyst support. So overall, I like to thank all the my team members, because all this work has been carried out by my research scholars. Without research scholars, it is not possible to execute any kind of research activity. So these are my team. This is the former team. All they are already graduated. Dr. Rekha is in now Delhi University. Dr. Aravind in Bihar College is an assistant professor. Dr. Maksud in scientist at IICT Hyderabad. Dr. Bhaskaran at South Africa, and Dr. Dhananjay also in the ad hoc teacher at Delhi University. And currently these are my team at Central University of Kerala. You are feel free to interact and come if you have any chance to come visit our lab. And these are my team. And I also thanks funding agency DST SCRB for the support, as well as our university for the funding support. And so overall, what I have shown is I have given an introduction about what is inorganic solid materials, particularly porous materials, how it can be visualized, especially framework materials. Then we have given introduction about aluminophosphate, how the meso-microporous aluminophosphate can be prepared, how it will be useful for isomerization reaction. Then we also talk briefly about how this kind of mesoporous material can be useful for the support for heterogenization. So preparing materials, it's quite easy. It is all under the solvothermal or hydrothermal condition, and even at any laboratory condition, it can work out. So it is very easy, and we can heterogenize and can be monitored through mostly with the gas chromatography. All the reaction can be. So this kind of material has the very good advantages. Recent years we have shown this kind of material as good for the carbon dioxide utilization as well as biomass conversion. We are also developing in our laboratory. Due to time limit, I have to restrict to the only few application points. So once again, I thank the organizing committee, that is Pattamundai College, for giving opportunity to share some of our research work. Thank you very much, and feel free to ask any question happy to interact and answer. Okay, thank you.
Thank you, sir. Thank you for nice presentation, sir. Sir, question answer session will be at the end of the second session.
Okay, sure.
Sir, I will
Yeah.
request you to be with us up to that time.
Yeah.
Now I request
Yeah.
Dr. Sunil Kumar Pradhan to give formal vote of thanks and brief analysis of the SAR's talk. Dr. Sunil sir.
Thank you, Professor Corrida. Very good noon to all of you. I, on behalf of Pattamundai College, thanks Professor A. Sakthivel for his marvelous talk, which he has delivered during the first session. And he has a lot of experience in doing works on these materials, inorganic materials and heterogeneous catalyst system in Laboratory School of Physical Science at Kerala. Also, he has a long experience in doing research work in different universities like Delhi University and at Central University Kerala and also at IIT Delhi. And his interest of work is your mesoporous materials. In this nice talk he has delivered just now, he has thrown lights about the zeolite-based composites of carbon dioxide utilization, biomass hydrogenation, and plastic degradation, which I hope will be useful for the undergraduate level students, and they will inspire from his talk and how to choose a career basing on these findings. And he has thrown a lot of lights into the works he has done during his research periods. And he has a diversified works during his career, like doing chemistry in universities, chemistry for different industries, which now the government and the governments are wanting that there should be collaboration between different industries and the intellectuals or researchers in chemistry. Nicely, he has done his career in such a marvelous piece of work. And in these slides, he has thrown lights about history of solid-state chemistry, semiconductors, classification of silicates, zeolites, quartz, and aluminosilicates, how they can be synthesized, and the structure of beta case, alpha case zeolite structures, and similarly the molecular C materials which he has synthesized in his laboratories, that is metal oxides, aluminophosphates, silicates, and MOFs, and important how these inorganic chemicals are used in petrochemical process, that is the application in different petrochemical industries he has deliberated in his talk. And similarly, preparation of different zeolites which are useful in your pollutions or controlling pollutions in different levels, preparation of zeolites, and excellent framework flexibility of heteroatoms substitution, nature of acidity, and limitation of mesoporous system, meso-macroporous systems, and how their properties are affected by tuning the functional groups, that is hypothermal, thermal, steam, and catalytic efficiency. And assembly of such active sites and their mechanical properties, how they are controlled, is just discussed by Professor Sakthivel. Polymers, surfactants, and good oxidation catalyst. And very important things about his talk is that he has delivered the talk about the BSc level chemistry, that is hydroisomerization of 1-octane, enoxidation of epoxides, 2-alkylation, oxidation of alcohol, which is useful for undergraduate students. And he has characterized the works therapy and FTIR, NMR, and cell technologies, which is very recent and modern technologies that is used by chemists throughout the world. And different reactions like asymmetric catalysis, Michael addition, aldol reactions, and carbon dioxide capture reaction, conversion of methanol to olefin, and thin film preparation is his topic of interest in his research. So from Pattamundai, behalf of Pattamundai College, I am extremely thankful to Professor Dr. A. Sakthivel for delivering a talk in this pandemic period, which will, I hope, will be useful for all the chemists and students and faculty members who have joined with us from all parts of the globes. And lastly, I thank Professor Dr. A. Sakthivel, and I request him to again join us during the question and answer session, which will be at the end of this second session. Now I request IQAC coordinator and convener of this seminar, Professor Dr. D. Parida, to introduce our next speaker, who will be talking to you from Guwahati, Assam. Thank you.
Sunil sir, thank you for your vote of thanks to Dr. Sakthivel sir. And now it's time to introduce in detail to our resource person of the second session of this webinar, esteemed Professor Dr. Prodeep Phukan, Professor, Department of Chemistry, Guwahati University, Assam. Of this session, who will deliver his talk on the topic surface functionalized magnetic nanoparticles for the catalytic applications. Sir, we are thankful to you to be with us and offer us by delivering your nice talk. Professor Phukan is presently working as Professor, Department of Chemistry, Guwahati University, Assam. He has completed his PhD from CSIR National Chemical Laboratory, Pune in 1999 and postdoctoral study at the University of Tübingen, Germany in 2002, 3, 7, 9 and 2010. He was awarded FRSC from Royal Society of London in 2019, Alexander von Humboldt Fellowship in 2002-3, Raman Fellowship, only one fellow from Northeast India in 2007, Best Chemistry Teacher Award in 2013, and many more. 28 students have awarded PhD under his supervision, and 6 students are working under him now. He already published 134 international papers and 3 number of patents. He has total 2,815 citations, 26 H index, and 73 I-10 index. This is our credit to get you as resource person for this webinar, sir. You may now deliver your talk to our respected participants. Dr. Phukan, sir. Sir, kindly unmute, sir.
Yeah, it's
and
fine.
deliver yours.
Thank you very much, Dr. Parida, for your kind introduction. So, could you see my slides? Could you see my slides?
Yes, sir.
Yeah.
Yes, sir.
Fine.
Yes.
So, thank you very much, Dr. Parida and his team. I'm principal of Pattamundai College and coordinator of IQAC for inviting me to share some of my experience and thoughts in this particular webinar. It's called Advanced Chemical Sciences and Their Applications. So I'll be talking about surface functionalization of magnetic nanoparticles for catalytic applications. And it was really, it's my pleasure to listen to Dr. Professor Sakthivel in the field of zeolite, and he has a very excellent way he explained different aspects of the zeolites. So I'm really enjoyed his talk. And now I'll talk a little bit different from zeolite. It's smaller, much smaller than zeolite, so nanoparticles. So in my talk, so you see what are the important. First, I'll talk about already Professor Sakthivel talked about heterogeneous and homogeneous catalysis. So I'd like to speak a little bit about the heterogeneous catalyst first. And this is the disadvantage of heterogeneous catalyst, requirement of large volume of material, and many times it gets deactivated. And this is the advantage, reusability, cost-effective chemical process, and it's actually a green process. And prerequisite for an active catalyst, number one is active catalyst site that already Professor Sakthivel has explained, and large surface area. So these are the major prerequisites of an active catalyst, other than many other factors. See now, so it's, you can say, what are the factors that affects the activity of a catalyst? It's mainly size effects, and that dependent, of course, that it always dependent on the active catalytic metals or catalytic component or which are there in the surface of the heterogeneous catalyst. Besides that, so this is major component is a size effect. The dependence of a global reaction kinetics on the size of the active particles. Then size effects are common phenomenon and are typically taken advantage in the catalyst optimization. So always, so this is typically taken into consideration while we do catalyst optimization. And most common explanation, small particles expose specific sites which are catalytically active with modified absorption properties. So always when catalytic reactions we carry out, so obviously you will go for always absorption through these catalytically active metals. So that is why it is very important. And the reason for these modifications could be either, it may be geometrical nature, it may be its corner or other irregular absorption sites where the catalytically active metals are situated, or in the electronic origin. For example, electron deficient effects in small aggregates interaction with the support. So these are typical phenomenon used for explanations for catalytic activity of a particular heterogeneous material. So then next we will go that, however, we simply cannot reduce the size, because we understood now the size of a catalyst is important because it is related to surface area to volume ratio. The heterogeneous catalyst, you simply cannot reduce the size. So that is why it's because they may lead to collapse of the catalyst structure, because you could see that the Professor Sakthivel has given, is clearly explained the catalytic a zeolite, the structure of a zeolite. So once that, if you reduce the size of a zeolite, for example, then you cannot keep on reducing the size, because it will finally collapse. It will lead to the collapse of the catalyst. So that is why we have to be careful in size consideration when we talk about synthesizing or designing a catalyst. Next, then what may be the best solution for a best possible catalyst? So that means production of a catalyst which are small in size, maybe it is in nanometer dimensions. So then in that case, we define it as a nanocatalyst. So it is a slightly different from that particular whatever generally heterogeneous catalyst we talk about. However, so then what is the nanocatalyst? A nanocatalyst is a substance or material with catalytic properties that has at least 1 nanoscale dimension, either externally or in terms of its internal structures. So this is a typical definition of a nanocatalyst. Then nanomaterials are more effective than conventional catalysts, mainly for two reasons. Number one, first, they are extremely small size, 10 to 18 nanometers, yields a tremendous surface to area to volume ratio. This one we will talk about again. Then also, when materials are fabricated on the nanoscale, the acid properties not found within their macroscopic counterparts. Then why this happens actually? So why nanomaterials behave in different way than the normal catalyst, normal material? So the reason is, major reason maybe, nanomaterials are actually, it falls in between molecules and the bulk. And when it is still in nanometer size, they are still unstable. So, and they have high energy and surface area to volume. So many other things are there, exposed side and lot of dangling bones. So that is why, so they were always active. So they want to have some kind of combination to go for stable structure. That is why nanoparticles are more energy, they have more energy, and also, so that is why they were active and they show different behavior than the bulk particles. Now it's a, see, for example, what we talk here, tremendous surface area to volume ratio. So let us explain what happens actually. You see, for example, you take a cube, 2 inches, 2 inches, 2 inches. So its volume is 8 cubic inches. Surface area is 24 square inches. Now reduce 8 full, now you reduce to 1. 1 inch, 1 inch, 1 inch. Volume is 1 cubic inch. Surface area 6 square inches. Now see, we have reduced the 8-fold volume, a decrease of volume. Say it is 8:1. You can see 8 cubic inch, 1 cubic inch, and 4-fold decrease in surface area. So surface area is 6 square inch. It's 4-fold. So finally, what happens? Partition of a big solid surface in smaller fragments lead to the overall increase surface to volume ratio. So this is an important aspect of a heterogeneous catalyst. So finally, you will see it decreases the surface to volume, increases the surface to volume ratio. That means more surfaces are exposed when you go for smaller particles. So high surface area to volume ratio is favorable for any chemical reactions. So these are actually surface area to volume ratio. You can see here the size. This is a cube 1 meter. You can see here 6 meter inverse. Then 2 meter, 4 meter, you can see if 2 meter it is 3, then you see 20 meter, it is 0.3. You see the difference, 1 meter and 20 meter. So it is a 400 meter square and it is 1 meter square. So finally you see the difference is quite high. So that is why the surface to volume ratio, denoted as SA volume or SA of volume, is the amount of surface area per unit volume of an object or collection of objects. Sorry. So next, you see shapes, tetrahedron, cubes, octahedron, dodecahedron, icosahedron, sphere. So they have different surface area to volume ratio. You can see here, even the tetrahedron has one of the highest surface area to volume ratio. However, here again, this surface area to volume ratio is not the only factor that affects the catalytic activity of a material, because as I told you, where the catalytically active metals are situated, like it's in edge or corner, where that is also another important aspect. So one of the important aspect of catalytic activity of a particular material is heterogeneous material is surface area to volume ratio. So this is one of the important aspect. So next, so let us have some example of nanocatalyst. Industrial enzymes, zeolites, what Professor Sakthivel talk about is zeolite also nanocatalyst. But what kind of nanocatalyst? They were nanoporous catalyst. When the pore volume of pore structures fall into nanometer scale, then it is called nanoporous catalyst. Zeolites are mostly nanoporous catalyst. And then transition metal nanocatalyst. The newer types, transition metal oxides, metallocene, asymmetric catalyst, then carbon nanotube, and many other. These are many other such. Actually, it has to be two kind of things. So either maybe internal structure is you can relate to the nanometers, nano dimensions, or external structures, means overall size. So these are the two aspects when you define a particular nanocatalyst. So let us have this is simple nanocatalyst. So then what is the difference between other nanocatalysts and simple nanocatalysts? As I told you, once you synthesize the material in nanometer dimension, that size is very small. So the problem is recovery of the catalyst from the reaction mixer is difficult, as they cannot be efficiently filtered out from the reaction medium, because in the filter paper itself, it goes inside or it goes with the solution, and also it sticks to the filter paper or membrane, then what happens? So then you will have there will be a big loss of the catalyst when you do recovery and reuse. Another problem is agglomeration of the nanoparticle during the reaction and separation process. So it will become bulk, or it will become bigger particles than catalytic activity reduces much significantly in a lower side. And so then how to change this aspect? Use of the support, that is number one solution. That you take a support like zeolite support or metal oxide support or clay support or carbon support. Then what happens? You take a support, this is the support. Then you take metal nanoparticles, this is a catalyst, and this support is silica, carbon, whatever it may be. Then what happens? You incorporate this metal in the surface of the silica or carbon or etc. Metal nanoparticles are embodied in the base material and hence they do not get agglomerated. So this is important. However, less surface are exposed. Large amount of catalyst is necessary for a particular reaction. Second solution is nanoparticle itself. You make a support. So in earlier case, you use silica, carbon, or such those things in mesoporous is meso dimensions. So then you use in as a support product nanoparticles. And here what happens? You take this is a core of the nanoparticle itself. Its catalyst itself is a nanoparticle. So now here two nanoparticles here. In this case only one kind of nanoparticle and another support. And here support itself is a nanoparticle and the catalytically active metal also is a nanoparticle. So you have a linker, then you hook these nanoparticles on the surface of the nanoparticle. So then in such cases, again, this is again nano, this is also nano. So finally, so it may not be possible to separate efficiently. Then what happens? If you use magnetic nanoparticle, it makes the separation and recovery much easy. So what happens if it is magnetic? Then you can put a magnet and see this is a solution. Then put a magnet, all catalyst will come to this particular magnet. So this is external magnet. So then simply you decant it, then you can separate the magnetic nanocatalyst. So commonly used magnetic supports are magnetite, megamite, cobalt ferrite. Okay. So many people use this magnetite Fe3O4, and this is sometimes they use, mostly they use, or this one magnetite or cobalt ferrite. Now let us go for some brief explanation how to modify magnetic nanoparticles. Number one, modification one, with pre-synthesized nanoparticles of a catalytically active metals onto the surface of the nanosupport. What happens? In this case, we synthesize a nanoparticle, then we have a magnetic nanoparticle support, then mix it, or somehow you immobilize on the support of the magnetic nanoparticle. Secondly, modification 2, in situ generation of the nanoparticles during the synthesis of magnetic support. So what happens here? You take the magnetic nanosupport as well as this catalytically active material, these compounds, then you combinedly both you generate nanoparticles during the synthesis of the nanosupport. So this is modification 3. On immobilization of the catalytically active metals through a linker. So this is actually mostly people they use this one. So I'll explain this. First you take a linker, then of course you have to synthesize the nanoparticle. This is a nanoparticle. Okay. Then this linker through this particular orthosilicate, then just throw this in. You put this on the support on the surface of the nanoparticle. Then here, so now this is a linker which got hooked onto the surface of the nanoparticle. Then you go for suitable ligand, or if this linker has a very good functionalized end, so we don't need to have a linker, otherwise you need some linker, then add the linker, then you have this kind of structure, then salt of catalytically active metal, then here you could hook the magnetic catalytically active metals on the surface of the magnetic nanocatalyst. Then, so another is the immobilization of catalytically active nanoparticles onto the linker. So this is the linker again, magnetic nanoparticle, and here suitable functionality, you add it, then get this nanoparticle. So here, what is the difference between this and this? Here, you take this salts, then make a metal complex here on the surface of the magnetic nanoparticle. And here what happens? You make a linker, use some metal nanoparticle, hook it on the surface of the magnetic nano support. So then linking functionalities you see here, there are different type of linkers. You can see here. So this is a magnetic nanoparticle. MNP means magnetic nanoparticle. If you take triethoxysilane, this kind of linker, carboxylic acids, phosphoric acids, bisphosphonates, then thiols, then amines, diols, dopamine. So these are the different kind of linkers many researchers used to use to make supported magnetic nanoparticles. Then here magnetic polymer core cell nanocomposites. First you take this core, this is a magnetic core, that means it is a magnetic nanoparticle, and this is a cell. Then finally you get a functional sites. That means you take the core, then do polymerization, then you must have, because in such case, this polymer coating on the surface of the magnetic nanoparticle protects the nanoparticle from agglomeration, and then on the surface you hook some catalytically active metals. So you see here, core contains the active ingredient, while the cell protects the core permanently or temporarily from the external environment. And in general, surface modification is done through a linker having appropriate functional group. This is another region, another example. You take the functional group, reactive polymer, then you make this kind of polymer core cell nanocomposites. And functional groups are there. So this is, for example, amine, thiol, aldehyde, active hydrogen, alkynes, etc. And this is example of, this is a very old example you see here. And they actually, during this particular time, the 2003, 4, 5, at that time, so this kind of magnetic nanoparticle supported catalyst started appearing in the journals. So this is one example. They have used this palladium NHC complex for synthesis of this Suzuki, for as a catalyst for Suzuki reaction, Sonogashira reaction, and Hack reaction. Then this is another example. They have taken this iron oxide nanocrystals coated with a thin layer of polymer. Then here, this is a functionality. Then they make this particular catalyst. So this is a catalyst with a color. Then they did magnetic separation. So they have used for this kind of Suzuki reaction. This is another. This is he is a pioneer in doing such thing, Christopher Jones, and he also synthesized this kind of this basic nanoparticles, which can be used for now and again reaction. And this is another CC bond formation reaction. This palladium catalyst for Sonogashira coupling reaction, and this is another. This is chiral primary and tertiary diamines. Then through this. So they have, so these are actually then Fe3O4. So they have hooked. Then finally they have done asymmetric direct aldol reaction. Then this is another example for Palmer reaction using this surface functionalized Fe3O4. This is carbon oxygen bond forming reaction. And then this is oxidation reaction. So they have used Syria and then gold catalyst. Then finally they get this image. And this is reduction. This is dopamine as well, I told you. Then they make this particular structure. Then nickel chloride, they have hooked on the surface of this particular surface functionalized magnetic nanoparticle. Then they did this reaction for hydrogenation reaction. This is another reaction, reduction using this this particular ligand. They have made this. Then finally magnetic nanoparticle, they hooked it through this phosphonate ester. This is phosphoric acid. Then they hooked it. Then they used this deuterium complex for asymmetric transfer hydrogenation reaction. So these are recent reviews. Chemical Society Review 2013, ChemCat Chem 2010, 14. So there are a lot of reviews. You can go through it, and then you can find many examples, many examples on magnetic nanoparticles for as a catalyst for different organic transformations. Now let us, these are background of work I spoke about. Now let us come to our work, how we started with and how we did reactions, how we modified the catalyst and reactions. So our interest was to high performance magnetically separable catalyst, study the effect of ultrasound during the co-precipitation method of nanoparticle synthesis, direct use of magnetic nanoparticle as a catalyst. So these are our main issue. So we have chosen cobalt ferrite as a possible nanocatalyst for our requirement. And so this is the cobalt ferrite synthesis. This is FeCl3 and CO2. This is a simple co-precipitation method, like how they also do zeolite or hydroxide. Then in presence of some potassium hydroxide or sodium hydroxide, some basic solution, base, then repetitive sonation at 60 degrees centigrade, followed by centrifugation. Then we got the black precipitated, then dried at 100 degree. Then after drying this, we took it in ethanol, then repeatedly we sonicated to get this particular, it's a kind of almost a transparent, it is a colloidal solution. Okay, so like this we made this nanoparticles. Then what is the advantage? You can see here what we achieved actually. So this is, of course, nobody has used till then. It is 2011. Till then, nobody has used sonication method for synthesis of such nanoparticles. Then what is the advantage or what is the key features of our nanoparticles? For example, nanoparticles are highly stable without any organic capping agent. So we have not used capping agents because most of the nanoparticles get agglomerated without the capping agents, because it caps the surface of the nanoparticle so that it does not get agglomerated. But in our case, somehow it was stable without any capping agent. Then solid cobalt ferrite nanoparticle can be easily dispersed in aqueous or alkaline medium. Homogeneous dispersion can be stored without any stabilizer for months. However, nanoparticles get agglomerated in other non-polar and less polar solvents like DCM, toluene, etc. Actually, till our synthesis, most of the nanoparticles behaves in the opposite way. They were not stable or they were not dispersible in alcoholic or aqueous medium. But in our case, and in most cases, since they have used capping agents, they were mostly dispersible in organic solvents like DCM, toluene, or other organic solvents. But in our case, we have not used any capping agent. Then still it is quite stable and it is dispersible in aqueous or organic medium. So this is advantage. That means we can do reactions in aqueous and organic medium. So this is a characterization. This is the first characterization we have done in 2009-10. So this is actually same picture. You see the particles, and this is EDX spectra, and this is mapping analysis. It gives finally, excuse me, it reveals the uniform distribution of the cobalt ferrite particle in the sample. So this one, And this is a TEM picture. And this is HRTM. It shows that fringes which confirms this structure of the cobalt ferrite. And this is X-ray diffraction pattern. And this kind of baseline shows that it is a nano range, and it is actually amorphous in nature. And this is a hysteresis curve which shows that they were highly magnetized. They were magnetically active. They were magnetic. They have magnetic character. And so this is ESR spectra. So this is a strong magnetocrystalline anisotropy. It shows this is a field dependent coercivity. It is a all magnetic. This is study, and this is interesting. We tried this kind of surface property of the magnetic nanoparticle. Surface basic sites on a metal oxide surface can be studied by electron acceptor such as DC, TC, and Q. So this is the tetrachlorobenzoquinone. Okay, so this is the TC and Q. So or 1,4-dinitrobenzene. You can see the structure here. Okay, and we observed a limiting amount of chloranyl. So this is a chloranyl absorbed on as synthesized. This one A was much higher than that MNP prepared by conventional process. So this is a conventional way. We have synthesized magnetic cobalt ferrite nanoparticles which are already known in the literature using some capping agents, and here we have used ultrasonic method. So you can see here their surface properties much better, means that surface polarity, it looks very high, better. It's because they absorbed more chloranyl on the surface of the magnetic nanoparticle. Then this is a stability study. It's immediately after synthesis, it's quite stable. After 1 month, slowly you can see here, the stability declines, and see now after 2 months it declines. Of course, during the synthesis, so this one we kept on a fridge without disturbing. So then only we could see this. Otherwise, if you keep on checking after 1 or 2 days, it will definitely precipitate out. Otherwise, this dispersion stays for 1 month. And this is absorbance against time. So and then now the question is why it is so stable in aqueous or alcohol medium. So this is aqueous solution. Okay. Now we see increase of surface polarity. So this already we need, when we reported this, we must prove that it has very high surface polarity. So this particular explanation shows that this particular cobalt ferrite nanoparticle has very high surface polarity. And secondly, water molecule or hydroxyl functionality might be entrapped in the magnetic nanoparticle, which acts as a stabilizer or binder. So that is another reason maybe. It's because it is due to repetitive ultrasonic treatment. Actually, according to our theory of ultrasounds, if you keep on irradiate any kind of solution under ultrasound, then inside the solution, there are some certain hotspot where temperature goes very high. Although the overall surface temperature of the particular solution is not very high, but they create some hotspots inside the solution. So that hotspot temperature goes up very high, even more than 500. So it creates disintegration of the water molecules, and that get absorbed onto the surface of the cobalt ferrite nanoparticle. And since that kind of aggregation takes place on the surface or inside the cobalt ferrite, there may be some cracks. And then, so this acts as a stabilizer for, and since increase the surface polarity, so it becomes stable. And this also, we have also studied the IR of the nanoparticle. You can see here. So this is B, this is A. B is the synthesized normal co-precipitation. You can see here, this is almost flattened. And here, you can see, so this peak shows the surface has a lot of hydroxyl functionality. So that is why it is more polar, and it is dispersible in aqueous or alcoholic medium. But since it is very highly polar, it is not dispersible in DCM or toluene or other solvents. You can see it is very interesting. You see here, it's so stable in aqueous. It is in ethanol. This is a magnetic bar, a very small magnetic bar. It does not attract. But however, if you shake with that magnetic bar, immediately after putting the magnetic bar, so this one, once I put the magnetic bar here, then immediately it does not get attracted. But of course, you have to shake it, then it will get attracted. And in DCM, what happens? Immediately it get acclimated and it goes to the magnetic bar. It get attracted in magnetic bar. So this experiment also shows that is quite stable solution, dispersion in ethanol or aqueous medium. Then, so first, then when we synthesize this kind of situation, we got, and you can see from here, so this one shows that it is a surface basic property. So we thought we should do some reaction which can be carried out under a base catalyzed condition. So that is why we started with the mechanical reaction. So this is a very simple reaction. You can see at 30, 25, 15 minutes. You get, and it is at 50 degrees centigrade. The yields are very high. And so many reactions we have done. So, and it was so at that time, this particular paper, this is Journal of Molecular Catalysis, it became a top cited paper award we got during 2001 as well as 2012. Even today also it has a very high citation because that time there was none this kind of catalyst which are stable in aqueous or alcoholic medium. Then this is separation you see, this is aqueous ethanol, this is aqueous ethanol plus magnet, and here you put some DCM, immediately it get attracted to the magnet. It's very clear. So that means you can very easily separate it. And this also we have already shown. And after separation, this 95, 92, 90, 88% up to 4 cycle, it is quite impressive. Still slowly, this activity of the catalyst goes down. There are two reasons, of course. One is surface property may be changed, and maybe some agglomeration is taking place. And then this is a nitro-aldol reaction we have done. So this reaction as well, so many, and this is a chalcone synthesis, aldol condensation, and this is separation of the catalyst that already we have shown. And then we started changing our focus to synthesize different type of cobalt ferrite nanoparticles. So when we took cobalt ferrite, then put chromate here, chromium oxide, then we have what we coated with silicon dioxide. And surprisingly, you see, so first what we took make the cobalt ferrite, then we put chromium oxide here on the surface, then we covered the surface. Interesting property we got. So this is, you see here, so this is the surface is covered by SiO2. It's very clearly seen in the TEM picture. And these are magnetic hysteresis, but in this case you see here, simple cobalt ferrite is very highly magnetic. Then this is oxide, it is magnetic. So magnetic property decreases when you modify the surface of the catalyst. So this is important and interesting observation we made. Once the surface is modified, the magnetic property decreases. Still, we want a catalyst which can be separated using an external magnet. So that much magnetic property is sufficient for us. Now, here interesting thing, this is the as prepared cobalt ferrite magnetic chromium oxide magnetic nanocomposite exhibit photoluminescence. So nobody reported such a phenomenon before. So it is possible to induce photoluminescence property only after annealing. Actually, we have done some annealing study. So found that annealing after annealing at 1000 degrees centigrade, photoluminescence property changes is imparted in the so this is a absorption spectra. This is fluorescence emission spectra. And you can, so since we sent to nanoscale, we have to do some cell experiment so that it's really can be used for some other imaging. So this is FP per nanocomposite was used for staining cultured HeLa cells for the fluorescence imaging of the detection of the HeLa cells. So this, once you put this nanoparticle, HeLa cells get illuminated, and then you can see here green fluorescent particles. And this is actually the TEM and fluorescence image of cultured HeLa cells after putting the magnetic this nanocomposite. And this is photocatalytic activity of the nanocomposite for degradation of methylene blue. So it is quite, since it is it shows the photoluminescence property, so we have degraded the methylene blue in aqueous medium. So then we synthesize some zinc sulfide nanoparticle. And so this is the characterization. So I'll not go for detail. And this is all characterizations. Then this is, of course, characterization to study the band gap. Band gap energy EZ corresponds to the absorption band, was determined from the absorption spectra, where steep increase in the absorption is observed. So this is a steep increase in the absorption. You can see here. So this one, this part. See here. Okay. And then so this is the relationship. B is the constant related, then E is LH nu, E is the band gap here. Then you can determine the band gap is 3.2 electron volt. And so then we have used this to particular material, zinc sulfide material, for degradation of methyl orange. You can see here in 20 minutes, almost the curve becomes flat. So this is 90 minutes, nothing of course is there. And so this is time dependent kinetic curve. And so this is the actually mechanistic effect that that is what explanation we have done. What happens actually that the photocatalytic property always dependent on the separation between the hole and the electron. That you must be knowing about semiconductor properties, electron and hole concept. And actually electron moves. And if we can separate electron from the hole, then only photocatalytic property of a particular material increases. In such case, what happens? Electrons and holes, they get separated. And if you can separate it out and you can create such a situation there where the electrons can be moved and it is a recombination of electron and the hole can be stopped, then we get this catalytic property. Then what happens? We have a cobalt ferrite and zinc sulfide, then it forms, then once this electron moves to upper layer, then finally this oxygen, and finally what happens? So this separation of the electron and hole takes place, and then finally we get this photocatalytic property. And this is photodegradation of methyl orange, zinc sulfate, nanocomposite. So I'll not talk in detail on this. So it is simple and it is in 20 minutes it gets degraded. Already we have discussed all these things before here. So then we synthesized some palladium nanoparticle. What we did, we took the cobalt ferrite, then palladium also in situ we have generated and made this particular composite. And see here, then we have done Suzuki coupling reaction. And this also again become a very highly cited paper during 2011 and 2012. And next, PD cobalt ferrite, we have done sonography reaction also later, and the same compound. And this is opposite thing we have done. What we did, cobalt ferrite embedded one-dimensional zinc oxide heterostructure. We have synthesized cobalt ferrite nanoparticle in presence of a zinc oxide heterogeneous. Interestingly, during the synthesis, we found such kind of growth. And this is a XRD pattern, this is XRD pattern, and finally, so this was used for degradation of the this photocatalytic catalyst. And this is, you can see here, this is a prior to annealing, after annealing, so the structure changes. So this is phenolphthalein degradation we have studied. We got this kind of property. And here we change this surface property. We have already this silicon, this oxygen, this kind of bone. And what we did, chlorosulfonic acid we have used, then surface functionalization we have done. Then we have made this, we have used this catalyst for oxidative bromine alkyne. So this is the reaction, this synthetic method. First, we made this catalyst, magnetic nanoparticle. Then we have done this surface coating. Then still OH is there. Then this is chlorosulfonic acid we have used, ultrasonic irradiation. Then this acid property has been introduced in the surface of the nanoparticle. So these are characterizations. I will not talk about details. These are all characterizations. And finally, this we have used for oxidative bromination. And so we have done many permutation and combinations. We found that acetyl water 31:1 ratio is the best solvent for this kind of transformation. Yields are 93%. It's very high after 24 hours. So these are different molecules that we have synthesized. Then what we did, we modified the surface property of this cobalt ferrite using some amine. Then this amine, then we have taken furfuryaldehyde. Then we made this compound. We made the SIF base. Then on this SIF base, then copper acetate was added. Then copper was hooked onto the surface of the nanoparticle through a linker. This is actually the surface of the nanoparticle. We made a complex, copper complex on the surface of the nanoparticle. Then this, so these are characterizations. I will not talk about more. And then, so these are of course characterizations, SEM image, you can see TEM image, and these are the EDX spectra. And so then we finally, we did, this is a channel reactions because it is a copper catalyst. So we have done several channel reactions. And so this is, so then this is a reusability. You can see here, it is very high. We could reuse up to 3 cycles, actually more than 3, of course, but we have done experiments up to 3 cycles. Then what happens? We have used this again cobalt ferrite surface functionalized particles to hook cuprous-iodide. You can see here, this is the methods. And first we made this cobalt ferrite nanoparticle. Then we coated the surface with silicon, this one. Then we have used MPTS. So then surface functionalization took place. Of course, here also, all this will come here. And then simple cuprous-iodide we have added because it is sulfur there. So cuprous-iodide got hooked onto the surface of the nanoparticle. So this is the nanoparticle, the surface of cuprous-iodide. So these are different, this XRD pattern and IR, all these things, okay, SEM. Then this is a mapping analysis. It shows that it is uniform distribution of the cuprous-iodide and other materials on the surface of the catalyst. So different metals, carbon, oxygen, silicon, sulfur, these are distributions. Okay. So different, you see, iodine and copper, cobalt, iron. So this shows that you see here, copper is about 17 weight% is there. Okay. So that means it is copper is there. And this 28 weight% iodine. And here, so this is the TEM image. Then so all the HRTM. So we will not discuss much about this. And so this we have used for oxidative elimination reaction. We could make this. So there, till then, there is no such catalyst. Nobody has used any heterogeneous catalyst for this kind of oxidative amidation reaction. So that is why we made this catalyst. Then we have done oxidative amidation reaction. There are several examples, and this is actually optimization experiments, which shows that. So this gives 100 degrees centigrade, 12 hours, TBHP, TMSO, it gives 89%. And here TBSP 12 hours, 80%, 87. But this is better because it is 12 hours and this 80 degrees centigrade. And these are the different molecules that we have synthesized. And this particular molecule is for fluorescence property. That is why we also did sensing property we studied. And this particular molecule shows selective. It can be used for selective detection of mercury from the aqueous solution. And these are the catalytic characterization. So this is a semi-maze. You can see very nice structures. And however, in this case, we observed some problem here. Since cuproside was hooked on the surface, and plus we have used the BHP, it's the oxidant, we found that slowly its catalytic activity declines when we go for repetitive use of the particle. But it is unlike other methods, other catalyst we have synthesized, but this particular catalyst is not very much useful for as a reusable catalyst for oxidative amidation reaction under this particular condition. And finally, I would like to conclude, magnetic nanoparticles were used directly as, used as catalyst as well as a support. Stable cobalt-free nanoparticles are prepared without capping agent. Functionalization of cobalt-free could be achieved by incorporating chromium, palladium, copper, etc. The ASP-paired cobalt-free chromium oxide SiO2 nanocomposite exhibit fluorescence property. The cobalt-free nanoparticles can be dispersed in ethanol and stable in ethanolic and aqueous solution. However, in DCM, no stable dispersion is possible. Nanocatalysts could be separated by using magnet. Cobalt-free magnetic nanoparticles are basic in character. Cobalt-free, this particular, the way we have synthesized, not all cobalt-free nanoparticles. Cobalt-free nanocatalysts could be used for various carbon and carbon heteroatom bond forming reactions. So I like to thank DST for financial support, Department of Chemistry, Guwahati University, IIT Guwahati, NEHU, and Guwahati University for analytical facilities. So these are the students, Kula, Sandan, Subhasis, Bishopran, and Mintu work in this particular area. And finally, you can see Kula is received this Green Innovation Award from International Institute of Green Chemistry and in Mumbai. And here I think he is a big man, I forgot his name. So he got a Green Innovation Award, and it is selected all over India. And since he has done many reactions on aqueous phase, so that's why he got Green Innovation Award. With this, I thank you very much. I thank you again, all the teachers of Pattamundai College, principal, and especially Dr. Parida for giving me an opportunity to share my work with you. Thank you very much.
Thank you, sir. Thank you for your fantastic presentation in this session. Sir, now I request Mr. Dr. Sunil Pradhan to give formal vote of thanks as well as give a brief analysis about the talk given by Dr. Phukan, sir. Dr. Sunil, sir.
Dr. Parida. And so, good afternoon to all of you. Professor Phukan has delivered a nice talk on surface functionalized magnetic nanoparticles for catalytic activities. he has thrown light on the a piece of research work which he has undertaken in different institutions by collaboration of his students. So in this particular article, particular piece of talk, he has given light on the important aspects of heterogeneous catalyst that has already been discussed by Dr. A. Sakthivel, and the rest the nanosynthesis of such catalyst is the prime attraction of Professor Phukan's talk. And the other important aspects are how the nanocatalyst can be modified and explained in terms of surface area volume ratio. He has thrown light to that. Again, how the size of the nanocatalyst is important in its properties. Next, industrial enzymes, zeolites, and transition metal nanocatalysts are the area of interest of Professor Phukan during his research work, and particularly in this talk. Transition metal oxides, nanocarbon tubes, how they can be recovered, and how supported materials can be used to improve their catalytic effect, that is discussed by Professor Phukan. And nanoparticles as a support for catalysts. Mainly he has coined around, that is iron cobaltite or cobalt ferrite as is a nanoparticle which is modified and with different supports and surface modified properties are developed by him, and how they can be used for different carbon-carbon bond formation reaction like Suzuki-Sonagira reaction, and carbon-nitrogen bond formation, carbon-oxygen bond formation, oxidative carbon-nitrogen cross-coupling reactions are shown beautifully by him during his entire talk, which I hope will be useful for undergraduate level students. And this is this research interest is now modernly accepted to all because of this interest in green chemistry. In green chemistry, these topics are very much useful, and different simple reactions like conversion of aldehyde to alcohol, reduction of some reaction by sonication techniques is also elaborated by Professor Phukan. And the different characterization method which he has employed during his research work or developing this catalyst is same TEM, EDX spectra, mapping analysis, TEM, XRD, ESR spectra, and UV visible spectra, which are the very fundamental things in developing a magnetic nanocatalyst. Surface modification of magnetic nanoparticles, their stability study, and that is how the stabilizers are added to such nanoparticles, and very simple reactions like Nobina-gel condensation, quasi-homogeneous catalyst, how, and the last part, he has given us the methods how it could be recovered, how this be recovered and recycled after the use of these reactions. So after this talk, I am extremely thankful to Professor Phukan, who have joined us from a long distance and given a nice talk, which I hope must be useful for coming researchers or young budding researchers and the participants who have joined from all parts of the world during this IQAC webinar of Pattamundai College. And I hope Professor Phukan, along with his team members who have done this beautiful work during his long career as researchers in that part of India, I must thank from Pattamundai College for his long life and happy family life during this pandemic period. Thank you.
Thank you very much.
Thank you, Sunil sir. Thank you, Sunil sir.
Yeah.
Thank you for your kind comments. Now the question answer session will be started. I request Professor Ranjan Kumar Gahan to to coordinate this
Your mic is unmuted. Dr. Phukan, you are unmuted. Muted. You are not audible. Hello?
Sir, now question answer session is started. I request Mr. Ranjan Kumar Gana to coordinate this session. And now there are only 2 to 3 questions in the chat box. Now I request our dear participants to put many questions to both the Professor Sir, and also they may ask directly question in the direct question through the Google, through the Zoom Meet by hand raise option. They may directly contact to Sir, direct contact to both these Sir. Now I request Mr. Ranjan Singhano to cooperate the session.
Thank you, Dr. Farida. Good afternoon, sir. There are some questions from the different participants, sir. Please answer of the following questions. From Gitarth Kumar Chakravarti, Phukan, sir. What is the effect of ferro and paramagnetism on the photocatalytic properties of a nanomaterial?
Actually, you see, question is a magnetic property and photocatalytic property is slightly different. Okay. So it must show some kind of photoluminescent property, magnetic nanoparticles. Then only it will say, like if you have a magnetic nanoparticle, so you must show some, like you must incorporate some zinc oxide or similar photocatalytic material, titanium oxide. Then only it will show the photocatalytic property. A simple magnetic nanoparticle like ferrite or cobalt ferrite, it will not show photocatalytic property. So it is you must add some photo sensitive materials, like as I told you, zinc oxide, then cadmium sulfide, like titanium. So these materials, it has to be incorporated on the surface of the magnetic nanoparticle. Then it will show the photocatalytic property. So actually it is not directly related to the magnetic property. So for making a particular material photocatalytically active, you must add some extra to the magnetic core. I think, is it fine?
Yeah. Thank you, sir. Thank you, Phukan, sir.
Yeah.
Sir, another question, Professor Sakthivel, sir. Why the catalytic activity of a material changes by the changing the synthetic techniques, sir? Please, sir, answer this question, sir. Sir, I can audible.
So shall I, maybe I can give some light on that particular aspect?
Yes, sir.
Okay, so what happens, you could see from the very beginning of my slide, I told there are 2 aspects of a particular catalyst. One, how the catalytically active material get exposed on the surface. That means whenever we synthesize a particular catalytically active material, the absorption property of the particular material get changed. In catalyst context, the absorption property means absorption of the reactant on the catalyst surface. But simple support, it may not act as a catalyst for many reactions. So in such cases, you must add some kind of material, catalytically active material. And so depending on the surface that get exposed to the catalytically, reactants, so it will actually direct the catalytic property. So that is why catalyst, depending on the synthetic methods, catalytic property changes because surface property of a particular catalyst, which are actually exposed to the reactants, get changed. Am I clear? Is it clear? Okay.
Thank you, sir.
Yeah.
Another question, sir, please.
Yeah.
In between the mesoporous and microporous,
Yeah.
in between mesoporous and
Yeah.
microporous, which is
Yeah.
more stable? The another questions from Vibhudatta Pandya, sir.
Yeah, so that one I think Sakthivel will be much better to answer this. so
Okay.
actually I don't want to comment immediately because I may not be very much right. Yes, Professor Sakthivel is online. So
Yeah.
Okay,
yeah.
okay, sir. Okay, sir. Just I communicate. Sir,
Yeah.
Sakthivel, sir.
Yeah, I'm there. Yeah, sorry. Actually, some
Sir,
disturbance.
one question, please, sir.
Yeah, tell me.
In between mesoporous and microporous, which is more stable?
Yeah, definitely the microporous is more stable because it is a better crystallinity. The microporous materials are more crystalline than the mesoporous. So obviously the microporous materials are more stable. To improve the stability of mesoporous only, we are making the meso-micro composites. So mesoporous is relatively less stable. So it will be stability wise, the microporous are much better stability than mesoporous, definitely.
Okay, sir. Thank you, sir.
I think some more question has been somebody asked. I think there is one more question somebody asked.
Another question, sir.
Yeah, somebody has asked.
Approximately 35% of the world GDP is influenced by the catalysis.
No, not that one. I think how the synthetic technique vary the catalytic property. I think Dr. Govinda Chandra, Govinda Chandra Bera. I think there is a question by the
heterogeneity of our materials.
Yeah. So I have thrown some lights. Professor Sakthivel can more explain.
Yeah. Sure. See, it is basically the synthetic methodology is going to you are going to tune the active sites by changing the synthetic methodology. So because see, if you talk about zeolite, the aluminum is the active sites. So how much aluminum you are incorporating? It is basically depends upon the synthetic method. Suppose if you do with hydrothermal methods, you are going to have the isomorphous substitution. If you are doing with the incipient wetness method, suppose if you do with the wetness methods, you will get a Lewis acid site. So it is like the nature of the active sites is going to be vary with the synthetic method, definitely. So in our case, we have varied the tetraethyl orthosilicate VPT technique, that is vapor phase transfer technique we put it. So in which the silica is going to be deposited on the surface. When the silica is deposited on the surface, there is going to be tuned the catalytic activity. The nature of the active sites, like more of brown shade acidic sites, is going to be generated on the surface. So it is one of the method, like how we are preparing a method that definitely is going to vary the catalytic activity. Definitely, one can vary. Obviously, I think even Professor Prodeep Phukan also very good expertise on that. Because the nanomaterial is making nanomaterial is nothing but a synthetic method, different way of nanomaterial making. That is how they are tuning the catalytic active sites. You are tuning the electronic property. You are tuning the structural property, coordinating property by varying the synthetic technique. So obviously, the synthetic method is a best way to tune the catalytic activity. That is, I think. Any other question?
Hello? Yeah.
One question, sir. Monalita Das.
Tell me, what is it?
Yes, sir. Approximately 35% of the world GDP is influenced by catalysis house, sir. Sakthivel, sir. Please, sir, answer.
Okay. See, you know that any catalytic process, it is depends on any chemical process. You know that 90% of the chemical processes depends upon the catalytic. It depends upon the catalyst. So definitely catalysts play a major roles, but it may not be what you have seen in the world GDP growth or anything. But it is known in the chemical industry. See, there will be normally always they will calculate the cost to the chemicals. If you are manufacturing 1 gram of any chemicals, then what is the cost? So that will be decided based on the raw material, everything. Obviously, ultimately it will contribute to the GDP, but in the scientifically we cannot say that each and every chemical process this much GDP growth is going to be influenced. We cannot comment as a scientist. We cannot comment. Okay. So, but definitely the catalytics because you see that, for example, simple aspect gasoline production by the thermal process before 1950s. All the gasoline production was only by the simply by the thermal cracking and vacuum distillation. These are the process. And after 1960 only, the Zeolite has been contributed for the gasoline production. Now you are having the gasoline, or you are having the olefin gas liquefaction, that is methanol to olefin. All this has been produced with the presence of catalyst only. That made that your gasoline cost is less. Now you know that all the market is depends upon the most of the chemical process in which everywhere the catalysts play a role. But it may not come into the clear picture. We cannot say that this is this much percentage of GDP is going to be contributed by the catalyst. It is very difficult to say from scientific point of view, I feel. I think Professor Phukan agree with me.
That's right. Yeah. And of course, actually, that is another thing that what Professor Sakthivel says, catalyst is an integral part of a chemical process. So you cannot avoid catalyst. So, and actually use of catalyst makes the chemical process much simple. So, and plus cost effective. So, and green. So, because the use of catalyst is a part of the green chemistry nowadays. So, definitely if you go for green,
friendly.
Yeah. So that is why most of the industries, they prefer catalytic cheaper method for chemical process. That is why maybe that industrial side GDP growth is there in chemical processes because of that use of catalyst. Whatever the process, they use catalyst. That is what Professor Sakthivel implied. So I have just added few points. Yeah. Okay. Next.
Somebody CO2 capture by mesoporous. See, the CO2 capture is basically as such mesoporous silica or alumina doesn't have the capacity because you should have surface basicity. But then once you functionalize with the amine functional group, that is, we can see there are synthetic amine like a propylamine, propyldiamine, those kind of amines are available. So if you functionalize amine, then they can have a very good absorption capacity to carbon dioxide and then convert it to carbonate, because those kind of amine functionalized we have used for, even I think Professor Phukan sir used for the nanoparticle capping and encapsulation also he has used, and we have used for many heterogeneous of homogeneous catalysts. So once you functionalize the either microporous or mesoporous material with amine functionality, it is a very good support for the CO2 absorption, especially CO2 chemistry absorption. It can be useful.
Yeah.
Questions from Swapnil Sudhir Rana. Sir, Prodeep Phukan sir, how is the material changes its property based on its structure? Phukan sir.
What question? Yeah. What was the question? How?
Based on how is the material changes its property based on its structure?
As I told you, yeah. Actually, that structure changed actually. As I told you, I have at the beginning itself, I have shown the surface property changes with the structural characteristic. So surface area is dependent on the what kind of structure of a particular material. So obviously, the surface area to volume ratio when changes, then obviously that surface property changes. That is why catalytic property or any property, it is highly dependent on the surface structure of a particular material. So particular, if you talk about a catalyst aspect of the catalyst, in such cases you will find that on the surface, what kind of material is there on the surface of a particular material. Again, that particular catalytically active material like copper, gold, silver, or anything, where it is on the surface, then whatever the surface, that particular point, which are more exposed to the reactants, those are more catalytically active. That is why, depending on the structure of the surface, that means structure of the entire catalyst, property can be changed. Maybe Professor Sakthivel also can give some light in that area.
Yeah, I mean,
Thank you, sir. Yeah, another question, sir. Suprabha Panga,
Yeah.
one of the participants. Between the polymers supported nanocatalyst and nanomagnets supported catalyst, which is more useful, easier for recovery and reuse.
Yeah.
Once again, the question, between polymer supported nanocatalyst and nanomagnet supported catalyst, which is more useful and easier for recovery and reuse.
Yeah. So again, I have seen this question between polymer supported nanocatalyst. I believe in such case, I believe we were not using non-magnetic nanocatalyst. Okay. Again, all these things, say polymer supported or non-supported, right? Magnetic supported, nanomagnet supported catalyst. So both cases, and particularly in polymer supported nanocatalyst, it is always dependent on the size of the material, recovery efficiency. So if the size of the material is very small, then recovery efficiency of the polymer supported catalyst will be, nanocatalyst will be less. So, but in such case, but in case of magnetic nanomaterial, recovery percentage are very high. Again, other surface properties, if you remove, definitely the entire catalyst is dependent on the surface property and what are the material exposed on the surface. And if you talk about the recovery efficiency and surface to area to volume ratio, in such cases, magnetic nanomaterials are more efficient for separation and reuse. That is my opinion.
yeah.
Thank you, sir.
Yeah.
Thank you, sir. Thank you once again, sir.
Sir, a request, sir.
Yeah.
Most of the questions put in the chat box are already answered.
Yeah.
Participant may direct interact with our resource persons by unmuting themselves. If anyone want to interact with our resource persons, they may directly unmute themselves and contact, interact with the resource persons.
Yeah, there is a question. Why do nanoparticles have special property? You can see one question.
Yes, yes, sir. Yes, sir.
Yeah, Madhusmita Das to everyone.
Madhusmita Das.
So what happens? So I give you a simple answer. See, question is anything like I'll go to basic our family problems. Okay, so I'll not talk about a catalyst now. Say for example, your our younger generations like son, my son, they were more active. Why? They cannot sit at a particular place. They used to do a lot of things, and sometimes you have to control them. It's because they have high energy. Okay, so that means in the world, energy plays a major role. Okay, it is simple. So that is why in nanoparticle nano region, the energy of all the particles are very high. So they were actually not very much stable. So that is the reason why they were not stable, because they were very smaller in size. So they were unstable because they have a very high energy and they want to combine with other things. So that is why then in nano region, these particles are very active. The energy is very high than the bulk material. Bulk materials are very stable, like old people like us. So we are stable. So now we have less energy than the younger one. So like same way, bulk material has much less energy than the nanomaterials. So there's energetically more active nanomaterials are active. And the other property, a surface again, that in a nano region, that always whatever the, like you know very well, conduction band to valence band, those transition takes place in a nano range. It is different than the bulk. Okay. So in such case, that particular transition again define the property of a nanoparticle. So because it is again energy, E is equal to H nu. So those kind of things combine the magnet, particular nanomaterial more active than the other. So anything?
Question. Question is, any questions from? Yes, anybody? Any applicants?
Sir, yes, sir. My question is,
Yes, you speak.
Yes, you can direct contact.
sir, my question is, as you told that capping agent is not used because the nano catalyst is capable to react. So
Yeah.
if we use capping agent, then
Yeah.
what happens, sir? Please explain.
Actually, what happens? Capping agents, if you use capping agents, stabilize the nanoparticle. Okay. And capping agents are generally, they have a very long chain, like you have surfactants, no? Like octyl amine or octanoic acid, like all big chains. So that will make the surface less reactive than the parent nanoparticle. So that is why they were more stable. So since surface is not much exposed, so that is why they were less reactive. That is why we have also later we used that silicon coating for capping as a capping agent. Okay. And in our case, initial phase, we have seen, since during ultrasonification, that nanoparticles, water molecules get disintegrated during the synthesis. So they actually adhere to the surface of the nanoparticle. So that also actually indirectly they use as a, they acts as a capping agent for the nanoparticle, so that it will not react to other. And secondly, once the capping agent interacts with nanoparticle surface has some property, like for example, if you handshake, what happens? You can keep the hand for long. So like that, a surface of the nanoparticle get entangled with another capping agent. So that means the surface energy is much reduced due to capping agent. So that's why they become more stable. Okay. Now, now surface is less exposed than the earlier. So in such cases, many times the catalytic activity goes little lower side. Okay. So then again, after capping agent, putting capping agent, still some of the surface of the nanoparticle get exposed. That is why they shows the catalytic activity in many cases. Okay, is it fine?
Yes, sir. Thank you.
Okay.
Ranjan,
Sir, from Govinda Chandra Behera, sir, how can I confirm whether it becomes a composite or becomes a supporting material so further? Please, Phukan sir. Please answer this
How do you
question.
confirm? No, it depends.
Yes. How can I confirm whether
Yeah.
it becomes a composite or supporting material so further?
No. Question is what is a composite? Is that a mixture of some more compounds? Okay, more materials. So if you have one nanomaterial and another nanomaterial, you are take one nanomaterial, then put on the support, then it's become a composite. Okay, and there are several composite materials. Okay, you mix it more materials, then you make a composite. That is one. Secondly, anything you can use as a support, like carbon, like silica, so anything. But only thing, what is the difference between a support and a simple composite, a simple material? That surface has to be, some functionalization should be there. So where the catalytically active material has to be added on the surface. So in such cases, that nanomaterials or any kind of material can be used as a support. So support is to provide stability towards the catalytically active material, so that catalytically active materials are, it does not get leached out from the surface of the particle. Okay, then so you can reuse the material. So anything you can use as a support until unless it is very highly stable. So it is any stable support you can use. Like clay, you can use as a support. Metal oxide you can use as a support. Carbon you can use it. Even polymer you can use as a support. So anything you can use as a support. Only thing, the support must have some functionality which can be used for further functionalization and stabilization of catalytically active material. Is it fine? Is it okay? Could you understand?
Yes.
Okay, fine. Thank you.
Yes, sir. Thank you, sir,
Yeah.
once again. And thank you all participants to join us for Grand Success of National webinar of Advanced Chemical Sciences and their applications. Thank you. Thank you all. Sorry. Lastly, a vote of thanks, formal vote of thanks to all the participants. Firstly, I would like to thank Professor Phukan and Professor Sakthivel from two extreme corners of the India, and for their nice presentation and giving their valuable time to the participants of the webinar. And they, what I find, they have a lot of research work during their career, and they have delivered very little things during their talks. If anybody interested, they can directly contact to them. Thank you, Professor Phukan and Professor Sakthivel, for operating Pattamundai College in organizing these webinars. And secondly, I must thank our principal, Professor A.L.N. Das, who has contributed a lot to organize the webinar for different departments in this college. And he is continuously hammering us for organizing such webinars, which I hope will be beneficial to researchers, students, and faculty members. And secondly, thirdly, I must thank the participants from different corners of world, around the different universities, colleges who have joined us during the webinar. And I hope they will also join us in future during further webinars if conducted by this college. And I must thank coordinator of this webinar, convener of the webinar, IQAC coordinator, Dr. Phukan, who has taken a lots of time to organize this webinar in time, and which is very much successful in my feelings for the different researchers, students, and faculty members. And I also thank the other IQAC members who have coordinated beautifully to arrange this webinar, Professor Subhasis Misra and Professor Jitendra Malik, who have coordinated to organize this webinar in this Pattamundai College. And lastly, I must thank the different faculty members of this institution and students who have participated in these webinars, and I hope it will be very much useful for their careers in future. Thank you. Thank you.
Now this session is over. Webinar is over. I also requested all the participants, they should not be worried about feedback. All the feedback will be sent to their email also, and all will get certificate. One should not worried about the certificate. The certificate will be given to all the participants after 2 days.
Okay.
Thank you very much.
Dr.
So
Farida,
I should
thank you.
leave.
Sir, I will request Prodeep sir to send his PPT, sir, please.
Okay, sure. Definitely.
I sent already.
Thank you,
Okay.
all of you,
Yeah.
for beautiful
Nice to meet you.
Nice
participation. Thank
meeting
you,
you.
sir. Now the meeting
Thank
is
you
over.
very much. Yeah.
Okay,
Thank you very much. Okay, bye. Bye.
Dr. Farida, okay, thank you. Okay, I'm leaving. Dr. Farida.
I think he